In example 3, we want to approximate the following square roots by hand using differentials. We don't have an explicit function defined here, but we can easily pretend that our f of x is the square root of x function. In this scenario, like I said, we're going to just pretend for a second that the function I'm talking about is the square root of x, and we're going to utilize differentials in order to approximate these two values. Let's start out trying to approximate 16.05. In this case, the square root of x, and in all cases, square root of x can be written as either x to the 0.5 or x to the 0.5. In order to use differentials, I'm going to have to calculate a derivative. It's easier to calculate a derivative if you're using the exponential version because the 0.5 can come out front. Then the exponent can be lowered by 1. 0.5 minus 1 becomes negative 0.5. If you'd like to rewrite this, one easy way to rewrite this is to have x of negative 0.5 be translated into the square root of x in the denominator, and you can leave 0.5 in the numerator. You could have also written this as 1/2 times 1 over square root of x. So that is a great first step, finding the derivative, finding the value. Let's focus on 16.05. If I want to find the square root of 16.05, what I do is I say, well, that is close to something that I know. That's close to the square root of 16. I know that the square root of 16 is equal to 4. This is a positive square root. So this is close to 4. So if I think about in terms of functions, what we're saying is that we're going to input a 16 into my function. That gives me out a 4. I might as well also, while I'm at it, since I know I'm plugging in 16, I might as well also plug in 16 into the derivative. And if I take 0.5 divided by the square root of 16, I end up with 0.125, or if you want to write that as a fraction, you'd write 1/8. I'm going to write this as a decimal. 0.125. If I want to find an approximation for 16.05, all I have to do is take f of 16 and then add f prime of 16 times the change in x. In this case, what that tells me is that the square root of 16.05, excuse me, is approximately equal to f of 16 was 4 plus the change was 0.125, f prime of 16 was 0.125, and the change in x is 0.05. If I calculate that, that tells me that the square root of 16.05 is approximately 4 plus 0.125 times 0.05. That becomes 4.00625, I believe. And again, you can type this into your calculator to confirm that you get something very, very close to that. And in fact, you do. 4.00625 is exactly what your calculator will give out if you round to 5 decimal places. If you rounded to more, obviously you can go out to more. So that's what is happening. We're going to do the same thing for 24. We say, well, what about 24? Or in particular, what about the square root of 24? What's that close to? You could do this with 16, but that's kind of further away than being close to the square root of 25. We all know that the square root of 25 is 5, at least the positive square root is. And therefore, my function, when you plug in 25, gives you a 5. Moreover, if you take the derivative function and plug in 25, you scroll back up here, 0.5 divided by square root of 25 would give you 0.1. So calculate that, you should get a 0.1. I'm going to copy and paste what I did here and just change the numbers. F of 24 is equal to f of 25 plus the derivative of f at 25 multiplied times the change in x. In this case, the change in x is 1. So f of 25 is 5 plus the derivative at 25 is 0.1 and d of x is -1. So change in x, we went from 25 to 24. That meant we went down by 1. This means that our approximation for the square root of 24 is 4.9. If you take the square root of 24, you indeed do get something that's pretty darn close to 4.9. About 4.898979, blah, blah, blah. So that's how we can utilize differentials in finding values that we may not be able to otherwise. Again, these gave me really good approximations for these square roots. And these square roots, if I had to do them on my own, would be hard to find. They'd get hard approximations for. So if we didn't have the computing power like we do today, we'd want these approximations, and we'll see later that it's useful even today when we do have really good computing power. I would like you to approximate the following two values by hand using differentials: e to the 0.05 and cosine of 3. Just to give you a hint, e of 0.05, that's close to e to the 0. And cosine of 3, well, 3 is pretty close to pi. So try approximating these things by hand.